How we doing? We doing? Questions by anything? We have a test Friday. We have a test next week. Okay. I'm gonna give you a test individually if you want.
Oh no,
I couldn't remember. I'm just teasing. I'll give you an extra one. Happy to do that.
give me an extra one. Can I get extra credit on it?
No. No, it's just more work.
That's the opposite of what I do.
Matter of fact, it's a requirement that you get no credit for that.
The numbers.
Oh, sure.
Oh, those are symbols. I thought you know it wrong. No, I just saw all the small writing.
All right. Did you get registered for?
Not yet.
There's issues with stuff, but did you get my email?
Yeah.
Okay, good. So let me know if there's any issues, but it should work. All right. Questions about anything at all? That's going to be the next handout that we do. So yeah, I sent that email. I forgot to go get the printout. And I was like, oh crap! I also forgot to email you too with it. So yeah, we'll start that here in a little bit. This is the last town that we talked about. So pardon me. Let's go through this example where we've got a differently defined inner product on P2. So notice that in this case, we're defining the inner product of two polynomials to be evaluate each of the polynomials at 0, 1, and 2, and then multiply those outputs and add them together. So kind of looks like a normal-ish inner product of things in R3, except that I'm actually using the polynomial outputs and then multiplying those together. We did the other one where we just said, take the constant terms, take the x coefficients, and take the x squared coefficients, multiply them together, and add. We did that one last time. And said basically, hey, that looks like the inner product on R3, the normal dot product on R3. This one definitely does not look like the inner product on R3. All right, so this is a little bit different. You should be able to go through and make sure that the 4 vector space axioms are satisfied. So remember, those 4 axioms were that you can do the inner product in either order. The inner product distributes over addition. Scalars, you can move to whatever one you want. You can pull it out of the inner product or put it on either of the inner pieces of the product. It doesn't matter. Those are all just straightforward. Go through and do it, right? If I want to check, for example, if I want to check that this inner product is commutative, what's the only thing that's going to change? If I do Q of X inner product with P of X, what would change in the output here? Yeah, we've just flipped the P's and Q's, but those are just multiplication of real numbers, so there's not any issues there, right? So, for example, checking commutativity is not a big deal. So the other pieces of those first 3 axioms aren't difficult to check. The 4th one's a little tricky, and in particular, the second part of the 4th one is tricky. So remember that the 4th part says, the 4th axiom says that the inner product of a vector with itself has to be non-negative. That part's not the tricky part. The tricky part is it says that the only vector, when you do the inner product with itself, that gives you the number 0 is which vector? The 0 vector, right? It's the only one that does. Okay. So if you were to look at this one, why am I not writing? Why is my pen not working? Why are you not working? Are you just pretending like you don't understand that it's connected? Try. Put it back on here. Yeah, you put it. Okay. Try this again. What are you doing? Way. Scroll. Why are you not working? Okay. Well, recording's not going to work today because I'm going to have to write it on the board. So, all right. Let's see. Do I have an extra copy? Sorry. I love technical difficulties. I don't know why it's not working. really does not like it. Oh, no. Now I have, of course. Sorry. Oh, where am I? Okay. So let's look at this example. Try this again. All right. The fourth one, if I wanted to do the inner product of a polynomial with itself, what would that look like for its output here? What would the inner product of a polynomial with itself look like here? Good. So yeah, so basically I'm taking each of those outputs at 1 for that polynomial and squaring it, right? You'd have p of 0 times p of 0 plus p of 1 times p of 1 plus p of 2 times p of 2. Since I've got a sum of squares here, what do you know about the sum of squares? It's always going to be positive, or it could be 0, right? It has to be non-negative, right? So no issues there. So again, first part of the fourth axiom, not too big of a deal to check, right? Hopefully that wasn't too big of a deal to check. Second part, though, says that the only way to get 0 out of an inner product of a vector with itself is to use the 0 vector itself, right? If and only if. Okay? Well, certainly if I take the 0 polynomial, I get 0. So the one direction is easy, correct? If I use the 0 polynomial, then p of 0, p of 1, and p of 2 are all 0, and I get 0 out. Okay? The other way is a little bit trickier. So if we assume that if I have the inner product of the polynomial with itself equal to 0, that would tell me that the sum of squares that we just came up with is equal to 0. Well, the only way that a sum of these squares can be 0 is what has to happen for each of the individual pieces, each individual term. They each have to be 0, right? So this would tell us that if we have the sum of squares as 0, this would tell us that I put in 0 for the polynomial, I get 0. I put in 1 for the polynomial, I get 0. I put in 2 for the polynomial, I get 0. Right? The only way I can get that sum of squares to be 0 is if each individual piece is 0. So now let's think about what we know from algebra class before this algebra class, back in high school algebra. I put in 0, I get 0. I put in 1, I get 0. I put in 2, I get 0. So at least how many roots does this polynomial have? It has at least, right? If I have p of 0 is 0, p of 1 is 0, and p of 2 is 0, how many roots do we have at least? 3, right? I've got 3 places where it crosses the x-axis. But what kind of polynomial is p here? Where does it come from? What is our vector space in this example? P2. What kind of polynomial is it then? It's quadratic, or it could be linear, right? Or it could be constant. But in particular, it's degree 2 or less, right? Well, how many roots are you allowed to have for a quadratic? 2. How many roots are you allowed to have for a linear? 1, right? So, can this be a quadratic function? No, it has too many roots, right? So what's the only function that could possibly, in this space, what's the only function that could possibly have more than 2 roots? Yeah, the constant polynomial that is the 0 polynomial, right? So since p of x is in P2, we must have p of x is the 0 polynomial. And I don't know why that jumped on me. There you go. So like I said, this one required a little bit more work to make sure that we had that fourth axiom verified. We had to use the fact that we know that degree 2 polynomials have at most 2 roots. This tells me that this polynomial has 3 roots. Well, the only polynomial in P2 that has more than 2 roots is the 0 polynomial. So this has to be the 0 polynomial. So this shows, well, this shows part of what we would need to show that it is an inner product. So let's see if we can use it. The first one should be pretty straightforward. If I want to do the inner product of 2 plus x minus x squared and 3 plus x, what would we have? What would the first term be? 2 times 3, yeah, 6. Good, right? If I put in 0 for x, I get 2 for the first one and 3 for the second one. The next one would be 2 times 4. And the last one would be 0. Okay, 0 times whatever that is, 7. Yeah. That's what a calculator is for, right? So we get 14 in that case. That okay? All right. So let's see if we can do part B and then part C. But I realized that we didn't do the definitions last time, but we did talk about it a little bit. We did talk about norm last time, norm or magnitude. In Euclidean space, we know how to do that. We do the square root of the sum of the squares of each of the components, right? But the reason that works is because the sum of the squares of each component of a Euclidean vector is just the dot product of that vector with itself. So for any inner product space, we can define the norm of a vector is the square root of the vector with its the dot product of or the inner product. Well, I should use inner product notation here. The square root of the inner product with itself. This is how we define magnitude, define norm. A lot of times we get rid of the square root because it causes issues when we're trying to do some computations. So and we'll do this later here as well. But a lot of times you'll see this written this way, and then I don't have that ugly square root in it. The magnitude squared is just the inner product with itself. And I believe, like I said, I think we talked about this last time with respect to Euclidean vectors, but when you do the distance between V and W, in terms of Euclidean vectors, we think about distance between the vectors as the distance between their terminal points when they're in standard position. And we said that between those 2 points, you could find the vector V minus W and take its length, right? That's exactly the same idea that we use here. The distance between 2 vectors is just the norm of the difference of the 2 vectors, no matter what the inner product is. Okay. So let's see if we can do these other 2 examples. For B, I need to do the inner product of this one with itself. Let's do that first. So if I want to do the inner product of 2 plus x minus x squared with itself, well, you already calculated what P of 0, P of 1, and P of 2 was up here in the previous part, right? So this is going to be 2 squared plus 2 squared plus 0 squared. Because we do P of 0 times P of 0 plus P of 1 times P of 1 plus P of 2 times P of 2. We get 8. Yeah, lady.
Can you explain how you got the values for part A?
Each individual one?
Yes, please.
Okay, so this 2 came from putting in 0 for x. That 3 came in from putting 0 in for x. So that's P of 0, Q of 0.
Okay.
This 2 came from putting in 1 for x. That 4 came from putting in 1 for x there. And then likewise for the 2's. Yeah, we're just putting in those values in for the polynomials. All right, so part C then, If I want the distance between those two vectors, those two polynomials, what do we need to do first? Going back up to our definition of distance, what do we need to do first? Yeah, and you do the difference of them, right? It says do the magnitude of the difference, do the norm of the difference. So 2 plus x minus x squared minus 3 plus x squared. Get negative 1 plus x minus 2x squared. So the distance between those two will be the norm of the difference. So it would be the norm of negative 1 plus x minus 2x squared. And then again, to find the norm of this, we'll do the square root of each of those function values squared. So we need to plug in 0, plug in 1, plug in 2, square those values, add them up. What do you get when you plug in 0? Negative 1, so I'll have negative 1 squared. What do you get when you plug in 1? I get negative 2, so you get negative 2 squared. And then finally, when you plug in 2, see that's negative 8. So you get negative 7. Is that right? Negative 1 plus 2 is a positive 1 minus 8. I think you get negative 7. 49, 53, 54. 54 has a 9 in it. What was that? 3 squared is 6. I don't really care if you simplify the square root or not. Calculators will do that for you. And the way I wrote that, it looks like I kind of wrote the cube root of 6, which is not. It's 3 times the square root of 6. What questions do you have on that? Yeah.
Can you explain how you got the numbers in this figure?
Under here?
Yeah.
So first thing I did is I plugged in 0. That gives me a negative 1.
For all of them? So like you plugged in 0 for like the whole thing and then you need the negative 1.
Yep, I plugged in this. Yeah, I need to plug. So I need to do. So this is my polynomial here, right? This is going to be my p of x, right? So when I do the inner product of p of x with itself, I'm going to do what I have up here, this part here. So that was weird. Put in the 0 for the p of x and then square it. Okay. So I put in 0 for x, I get negative 1 squared. I put in 1 for x, I got negative 2 squared. Does that make sense?
Yeah.
Okay. Other questions? It's just however the inner product is defined. That is not the right. No, that is not the right problem. Okay. Apparently, something has happened where it deleted off the top of my number here. All right, so let's look at the next example that we have. This one, rather than having an inner product given to us, we have some values given to us. So this tells you that the inner product of u and v is 2. V and w, that inner product is negative 3. U and w, that inner product is 5. Magnitude of u is 1. Magnitude of v is 2. Magnitude of w is 7. So notice we're not given any specific vectors. We're not giving we're not given any specific inner product space. All that we know is that we have an inner product space, and it gives us some information about those three vectors, how they interact with each other as inner products. And it also tells us something about the inner product with the vector with itself. Okay. Now, we write our inner product with our bracket notation, but probably if you've learned inner product before, you've written it with a dot notation, right? Well, if I think of that dot as ordinary kind of multiplication idea, what would you do if I wanted to multiply these two things together? FOIL, okay? And that works because dot product, inner product distributes over sums, right? So I can write this as u dotted with v plus a u dotted with w plus a v dotted with v plus a v dotted with w, right? That would be what foiling would look like. FOIL works. FOIL works with inner product with respect to sums. Okay? So this is how you would do it with dots. If I wanted to do it with the inner product notation, you would have u inner product with v, u inner product with w, v inner product with v, v inner product with w. And do we know all those values? Yeah, sure do, don't we? What's u dotted with v? 2. U dotted with w? 5. How about v dotted with itself? Yeah, it's 4, right? Because it's the norm squared, right? And then v dotted with w is -3. So we get 8 when we add that all together. Obviously, the other 3 were given to us. The only tricky one, I would say, was doing the v dotted with itself. Remember, magnitude or norm squared is the vector not dotted with itself. That one make sense? Do you see any difference in what we would do in part B? What's the only real different thing we would do? Multiply the scalars and pull them out, right? And we can do that, again, with inner product, because scalars we can just move out in front, correct? So what would be your first inner product, or the first term that you would really need to compute here? So if you're thinking about kind of foiling it, what would you have? Yeah, 6 and then a v, and like you said, like Ben just said, v times a w, not a w, a u, and the times is inner product. So the first term would be 6, because I do the 2 times the 3. I can pull the constant out, and then I'm left with v dot w, or v dot u. I keep saying w. What would the outer terms be in your FOIL? Yes. 2 times 3. Right? I'm taking this one. I'm doing the first terms, right? Thinking about your FOIL here. I'm multiplying the first terms together. So I'm doing the 2 times the 3. What would you get for your outer term?
4.
Good. 4, and then v inner product with w. What would you get for your inner term? -3. Yeah, u, good. Please don't write it as u squared. That doesn't make any sense. Norm of u squared is fine. Don't write it as u squared. The vector times itself doesn't make any sense. What's the last one going to be? Good. -2 uw. And do we have values for each of these now? And what's the v inner product with u going to be? Oh, it's 2, right? We know the inner product is commutative. So v inner product with u is the same as u inner product with v. So this is 6 times 2. V inner product with w is -3. The inner product of u with itself here is 1. I'm going to write it as 1 squared just to emphasize again that that's the square of the norm. And then the last one, u dotted with w, is 5. 12 minus 12 is 0, minus 3 minus 10 gives me -13, if I did the arithmetic right. Again, essentially, all we're doing is FOIL. Something you did back in algebra class in high school, I hope. Maybe you did an algebra class in middle school. I don't know. I don't know if you took algebra. Teacher got fed up with being in grade school and gave me an algebra book in 4th grade, so. That was a pain. It's fine. For those, however, I will say, for those of you who are going into education, for the love of God, don't do what they did to me in grade school. So they didn't really know what to do with me, so I just got sent out in the hall with more work. I spent most of my life during math lessons in grade school out in the hall. So don't do that. From a social standpoint, please don't do that to them. Don't isolate them because they are doing something at a higher level. To you, wasn't so funny to me. Yeah, don't do that. Okay. In any event, let's do so the next one is just kind of an extension of doing foiling ideas, right? If you think about, again, I'm not going to write this out on the screen here, but if you had something like 2x minus y plus 4z, and you want to multiply it by 2x minus y, you're just doing the distributive property again. You're just kind of doing it on steroids, if you will. I need to distribute this to all 3 terms, right? And then do the same thing with the other one. Do that one, that one, that one. I have to do all the multiplications, right? So what will we get in this case? Yeah, 4u with u. Okay, plus uv. You're going to go do it the other way. That's fine. That's okay. Either way it works. It doesn't matter. Good. Or technically it's vu, right? Okay. Good. Yeah, that's fine. Good. You're exactly right. You can write it in either order because the inner product is commutative. I'm just writing it this way because technically that's on the left side of the other one. Everybody okay with how we got those? Just doing this distribution. Alexis did the u with the u, the u with the v, and then the v with the u, the v with the v, the w with the v, and the w with the v. Okay. As long as you get all 6 multiplications done, you're good. Doesn't matter what order you do it in. And now again, do we have all of these values? Yeah, better have, otherwise it's a really bad problem. UU will be 1 squared. UV was 2. VU is also 2. VV is 2 squared. WU is 5 again. And WV is -3. I'm not going to bother simplifying the arithmetic. That one okay? All right. Let's do D. I'm going to, actually, let's do E, because if I can do E, we can do D. And the other two are, if we do E, we can do D and F. Either of those is the same. Let's do E. If I want to attack something with the magnitude of a vector, what do I need to compute? Good. So again, oops, don't need that bracket. If I want to do the magnitude or norm of a vector, I need to do the square root of the inner product with itself, right? So when we do the inner product with itself here, what do you get? For WW, good. Yeah, a couple of 2WVs, right? and then plus the VV. Notice the term in the middle, I got the same term twice, right? I got a minus 2WV and a minus 2VW, but we know that it's commutative, so we just get a 4WV or a 4VW, whichever way you want to talk about it, right? And again, do we know these values? Yeah. W with itself is 7, so we'll get 4 times 7 squared. VW is -3, and VV again is 2 squared. And again, then whatever that turns out to be. It better be positive under that square root, otherwise we have an issue. Going okay? This is why we want to make sure that when we do a vector product with itself, an inner product with itself, I should say, that I get a positive number because I want to be able to take a square root and identify some sort of a length. This process okay? All right. This last one is basically playing around with the same ideas. This one says that if I want to do 1/4, if I can rewrite the inner product of U and V as 1/4 of the norm squared of the sum minus 1/4 of the norm squared of the difference. If you think about how you typically prove identities, whether it's in this class or say a trig class, usually you'll start with one side and work with the other. And usually the side you want to start working with is the more complicated side. So which side do you think we really want to work with? The right is more complicated. At least I think it's more complicated. So if I start with our 1/4 magnitude of U plus V squared minus 1/4 magnitude of U minus V squared. There's a 1/4 in both terms, so I'm just going to pop it out. What's another way to write norm squared? So square root is if I didn't have that extra squared on there, right? So the squared, you'll scale the square root off. So yep. So I'll just do the inner product with itself. Since I have magnitude squared or norm squared, it'll kill off the square root, right? And then just like what we've been doing, we can basically FOIL out this thing. The first terms will have a U inner product with U. When I do the outer and the inner, what do you get? Yeah, we'll get a 2 UV. The outer gives you a UV, the inner gives you a VU, but again, the inner product's commutative, so we just get 2 of those. Then we get a VV. What's the only thing that's going to change in the second one? Yeah, the sign in the middle is going to change, right? So in this one, we'll have a minus UU minus 2 UV. It's a V plus VV. Good grief, what is with the technology today? Right? What happens now? Yeah, distribute the negative through. After we distribute the negative through, what happens? Yeah, Well, it's ended up simplifying down to 4 UV, right? The UU's will cancel, the VV's will cancel, right? So this will simplify all the way down to 1/4 of 4 UV. So we end up with just UV. This particular example, again, was just playing around with the idea that we can rewrite the square of a norm as the inner product of a vector with itself. Questions on that one? All right. So last time we talked about 3 reasons why we care about inner product. 2 of them are kind of related to each other, right? We said that we cared about finding lengths of vectors, and we also said that we cared about finding distance between vectors. But the last thing we said, we also want to be able to do angle between 2 vectors, and we haven't done that yet. So that's what our goal is for this particular section, is to handle looking at angle between vectors. And then an extension of that is orthogonality, which is still angle between vectors. It's just a special case of what the angle is. And if you've had Calc 3, you probably already know what orthogonal means. All right. So to make angle work, we need a particular special property. So do this off on the board because I don't really care if you write this down or not. Let's do this in the 2-dimensional case here. So let's say I have vectors, 2 vectors here. This is the point x1, y1. This is the point x2, y2. And I want to figure out this angle in here. Again, don't really care if you write this down because I'm just going to go through and why we are going to get what we have here for angle. Okay. That vector again, we can get as x, we have it written as x1 minus x2, y1 minus y2, the way I have it written, right? If I want to figure out, if I know what x1, y1, and x2, y2 are, I know the lengths of all 3 of these sides. So we can use the law of cosines to be able to get us the angle that's in here. All right? So remember, law of cosines basically looks like your Pythagorean theorem to start. And then we have to adjust for the fact that we've got a non-right triangle sometimes. Basically what that does. Notice that this is the Pythagorean theorem with theta is 90. Right? It's exactly the Pythagorean theorem when the angle is 90. Okay? All right. So if I go through this, well, this is my C. So I end up with, and again, we're squaring the length here, right? So I end up with x1 minus x2 squared plus y1 minus y2 squared on the left-hand side. On the right-hand side, we end up with what? I get x1 squared plus y1 squared, right? Then this part becomes, this is the length of A, so this is square root of x1 squared plus y1 squared. I'm running out of board. This one is square root of, oops, I forgot a term, didn't I? I forgot my b squared. We got my b squared in there too, right? And this will be square root of x2 squared plus y2 squared, and I've got cosine of theta on the end. I know I'm going through it quickly, but I want to get to the point. Okay. All right. So, in any event, this is what this looks like. Okay? Notice when you FOIL out the left-hand side, you'll get an x1 squared. I subtract that over, it's going to cancel with this one. I FOIL this one out, I'm going to get an x2 squared. It'll cancel with this one. All right? Same thing will happen here with the y1s and the y2s. They'll end up canceling. So the only thing you're going to be left with on the left-hand side is a minus 2x1 x2 and a minus 2y1 y2. It's the only thing that's going to get left on the left-hand side. Correct? On the right, and then when we divide to solve for cosine of theta, I'm going to divide by minus 2 in the product of those two things, correct? So I'll divide by negative 2 square root of x1 squared plus y1 squared square root of x2 squared plus y2 squared. And that'll be times cosine of theta there. The negative 2's will cancel on top and bottom, right? What do we notice about what's left on top? I've got x1, x2 plus y1, y2. Relative to these two vectors, what is x1, x2 plus y1, y2? The inner product. On bottom, we're left with what? The magnitude, the norms. Yeah, exactly right. I got norm of the product of each of those. So notice on top, we end up with the inner product of the two vectors. On bottom, we end up with a product of the norms of the vectors. And then to find the angle, we need to be able to do the inverse cosine, correct? If I want to actually find what the angle is. I've lost my pen. Lost my pen. Okay. So in order to be able to do the inverse cosine, what do I need to make sure happens relative to that fraction? What does the fraction need to be? I want to actually be able to compute the inverse cosine. What does the fraction need to be? In between negative 1 and 1, right? If I have a cosine of an angle, it's always in between negative 1 and 1. So in particular, I need to make sure that my inner product is less than or equal to the product of my magnitudes in an absolute sense. So that's exactly what the Cauchy-Schwarz inequality says, that in an inner product space, the absolute value of the inner product of two vectors is always less than or equal to the product of their norms. That's what the Cauchy-Schwarz inequality says. That's the important part of that particular inequality. I'm going to send out, the proof is not horrible, but I don't want to spend the 5 minutes of the class time to talk about what I did. I will send out a proof so you can see what the proof looks like. Okay. All right, so let's talk about some of these other properties that we have for length and distance here. So 1 and 2 we already know. That's just a consequence of the axioms, right? Right. So this is literally a consequence of axiom 4, right? Because we define length in terms of dot product with itself, inner product with itself. Okay. 3 is not bad, because if I want to do the magnitude or the norm of a vector with itself, again, that's square root of inner product with itself, right? What can you do with each of the k's relative to the inner product? Take it out, right? I can take out the first k, pull it out in front. I can take out the second k, pull it out front. So in front of this inner product, what can I write? K squared. And then again, when you do the square root of a square, you don't just get the value, but you get absolute value. So this becomes absolute value of K, square root of the inner product of U with itself. Square root of the inner product of U with itself is the norm of the vector. That one was not too bad of a proof. But then again, this works for any inner product space, and it does exactly what you would think it would do. If you think about how you learned vectors, if I do a scalar times a vector, you think about it changes the length of that vector by that scalar, right? If the scalar happens to be negative, it flips the direction, but the scalar itself changes the length of the scalar, or the vector by that scalar, right? That's exactly what this says. And it works for any inner product space, not just Euclidean vectors. This next one here is what we refer to as the triangle inequality. The reason why we call it triangle inequality, if you think about how you geometrically or graphically add two vectors together, you do tip to tail, and then put in the resultant vector, right? This is exactly how you do it graphically, isn't it? What kind of a shape did I just make? A triangle. Literally, what does this say in terms of a triangle? The sum of the two sides of any two sides is at least as big as the third. Which makes sense, right? Learned that back in geometry class. The proof of this also isn't too bad. It also involves the Cauchy-Schwarz inequality. So I'll send that one out as well when I do the proof of the Cauchy-Schwarz inequality for you, so that we don't take up the class time for it. All right. You should be able to go through these next ones and basically understand how these are just rephrasings of the first parts that we just talked about. And in terms of the vector, the inner product space axis. So think about these for next time. These this 5, 6, 7, and 8 here. And then we will get farther along and do the angle formula, which is what we talked about for the Cauchy-Schwarz inequality and why we cared. Okay. All right. So we'll do that next time. See you on Friday. Have a good one. I hope registration issues